Hello everyone, and welcome. You've all heard the golden rule of statistics hammered into your brain since day one. Correlation is not causation. It is the ultimate intellectual stop sign. We see a beautiful, tight correlation in our data, and we are immediately forced to stop and say, but we can't say one causes the other. But if correlation isn't causation, then what is? If our standard statistical tools can only tell us that two things move together, how do we answer the questions that actually matter? How do we move from seeing patterns in data to understanding what would happen if we intervened in the world? Let's start with an intuition. Imagine you see wet grass in the morning. Two possible causes explain this: rain or an automated sprinkler system. An association graph would just draw a line between wet grass and rain, and another between wet grass and sprinklers. It says, these things simply occur together. But a causal graph draws an arrow from rain to wet grass, and from sprinklers to wet grass. It says, rain produces wet grass, sprinklers produce wet grass. The difference is direction. Association captures passive observation. Causation captures active intervention. We use the do operator to mathematically denote forcing a variable to take a value. Formally, a causal graph, specifically a directed acyclic graph, or DAG, is built of three parts. Nodes represent variables. Directed edges represent direct causal relationships. And it is acyclic, meaning there are no feedback loops. The core distinction of a causal graph is stability under intervention. If you break an arrow, or physically disconnect a mechanism, the remaining graph predicts exactly how the system reacts. Now let's bridge the gap between visual intuition and rigorous probability theory. In standard probability, we describe data using a joint distribution. By the standard chain rule of probability, we can decompose this into a product of conditional probabilities. But this factorization is causally blind. It is a mathematical identity that doesn't respect how data is generated. A causal graph imposes a structural constraint called the causal Markov condition. Each variable is independent of its non-descendants given its direct parents. This yields the causal factorization based on localized parent sets. Notice something critical. Wet grass depends exclusively on rain and sprinkler. It does not directly depend on season. This is a testable implication. Now, what if we intervene? The do operator means we physically alter the system. Graphically, doing R means we surgically cut all incoming arrows going into rain, freeing it from its natural causes. Because we cut the arrow, season no longer dictates rain. This leaves us with a modified system where we can calculate the exact impact of an intervention. Using the adjustment formula, people often ask, why are we restricting ourselves to directed acyclic graphs? Why can't a causal graph have feedback loops? Let's break down the logical and physical reasons why a causal graph must be directed and acyclic. Reason 1. The arrow of time. Fundamentally, physics dictates that causes must precede their effects. If variable A causes variable B, then A must occur before B in time. If we permitted a cycle where A points to B, and B loops back to A, each would have to happen before the other, which is a structural time travel paradox. Reason 2. No self-causation. A cycle implies that a variable can be its own ancestor, leading to logical absurdities. For example, consider the classic economic model. Hard work causes wealth, and wealth causes hard work. If you intervene to increase hard work, wealth increases, which loops back to expand hard work infinitely. In reality, we resolve cycles by introducing time steps. Hard work at time t affects wealth at time t plus 1, which subsequently affects your hard work at time t plus 2. Reason 3. Causation is asymmetric. Why arrows instead of simple lines? Because association is symmetric, but causation is not. Rain causes wet grass is a true statement, but wet grass causing rain is completely false. Therefore, to map real mechanics, our graph must remain a directed acyclic graph. We now arrive at the core machinery of causal graphs. Every complex network on Earth, no matter how large, is built from just three structural combinations: the chain, the fork, and the collider. Think of these as the fundamental atoms of causal inference. Let's isolate the first structure, the chain. Here, A influences C exclusively through an intermediary mediator. B. Information flows freely from variable A to variable C through the middle variable. For example, higher ice cream production occurs during warm outdoor temperatures, which in turn drives higher beach attendance. In raw observational data, ice cream sales and beach attendance are highly correlated. However, if we condition on B, meaning we control for outdoor temperature by blocking this middle node, the pipeline is closed. Once you know the temperature, ice cream data provides zero new information about beach attendance. In a chain, conditioning on the middle variable blocks the path. The second atom is the fork. Here, B is a common cause of both A and C. This shared ancestry transmits baseline associations backwards through the branching arrows, creating a deceptive, spurious correlation between its downstream effects. For example, a child's age causes their shoe size and independently causes their reading ability. If you look at unadjusted raw data, shoe size and reading literacy are strongly correlated, but big feet do not cause literacy. When you condition on the common cause, age, by comparing only children who are exactly 8 years old, the correlation completely disappears. This is the definition of confounding. Conditioning on a fork blocks the path. The third building block is the collider, and it behaves in the exact opposite way. Here, B is the common effect of two completely independent causes. In the general population, being born with natural talent and experiencing pure luck are entirely independent variables. The path is naturally blocked. Because the path is naturally blocked, talent and luck don't covary. But look what happens if you condition on the collider by looking only at successful Hollywood actors. If a celebrated actor completely lacks talent, you immediately infer they must have been incredibly lucky. Conditioning on a collider opens the path, creating a spurious correlation. This is selection bias. Let's anchor these rules using a permanent summary table. For a chain or a fork, variables A and C are raw correlated, and conditioning on the middle variable blocks the path. For a collider, A and C are naturally independent, but conditioning on the middle variable opens the path, introducing bias. Master this structural map, because every complex causal path reading rule we explore next is built from these three interactions.